GeopByte.
Welcome to GeopByte. Today we will be discussing about our second unit, that is units and measurements. This is a very simple and an easy chapter, but it's a very important chapter too. What is unit? What do you know about unit, or what do you mean by unit? Suppose if I'm giving an example, I'm asking you to get me some onions and chilies from a shop. You go and tell the shopkeeper that 2 kilograms of onions, 2 kilograms of onion, or some 100 grams of chilies. Now, I'm asking you, what's your height? I'm asking you to measure your height. Some will tell that it's 161 centimeter. Some will tell that it's 5.3 feet. So, this 200, 161, 5.3, these are just numbers. These won't give any physical meaning. If I'm asking you what is your weight, if you tell it's 60, there is no meaning in it. The person who is hearing can assume by his own. Like he can assume it as 60 kg, even he can assume it as 60 grams. So this kilogram, gram, centimeter, feet, seconds, these are the units. Only when these units are with these numbers, this will be a meaningful one, or else there won't be any meaning to it. So, a unit can be defined as measurement of any physical quantity involves comparison with a certain basic arbitrarily chosen internationally accepted reference standard. So this is known as what? Unit can be defined as this. So before, scientists used different types of unit systems that are MKS, FPS, then CGS. In MKS, this is represented in meters. This mass is represented in kilogram, length is represented in meter, and time in second. In FPS, it's represented in foot, mass in pound. In CGS, it's represented in length represented in centimeters and mass represented in grams. So these were the different unit systems which scientists used before. Like, to make you understand, if I measure a thing, I measure certain length and I am telling it as 1 meter. And a person using CGS system will write this as 100 centimeter. So in this system, this will represent this physical quantity in centimeter. Similarly, if it is in this system, FPS system, that person may represent it feet. Or in this system, 1 meter only. So later, scientists came up with an internationally accepted unit, which is known as SI units. So this will be very important. That is, now from now onwards, whatever you are representing you should represent it in SI units. Now these units are classified into two. One is fundamental units and the other one is derived units. In SI system, there are 7 fundamental units where length is represented in meters, mass in kilograms, then time in seconds, current in amperes, then luminous intensity, in candela, temperature in Kelvin, and this molecule or atoms or whatever in mole. So these are the 7 fundamental units. These fundamental units we can't derive from anything. It will be already there. Whereas in derived units, these fundamental units are also known as base units. So these derived units are obtained from these things. From your lower class, you know that velocity is equal to distance or displacement by time. What is the unit of distance? It is meter. What is the unit of time? That is second. So the unit of velocity is meter per second. Similarly, if I am taking volume, suppose I have a cube of side A. The volume of the cube is A cube. That is, each side, unit of each side is represented in meter. So the volume is meter cube. Or if I am representing density, that's what? Density is equal to mass by volume. That is kilogram per meter cube. So all these are derived units. These all are derived ones. So now if I am asking you to measure your height, or suppose I am asking you to measure the length of this duster. You may take your normal scale, or you may take a tape and you may measure it, and you may tell it it's around some 12 centimeter or 15 centimeters. Suppose I am asking you to measure the distance of a faraway stars or planet. How will you measure? How can you measure? In such cases, we are using parallax method. To make you understand what this parallax method is, I will give you an example. Suppose this is a marker. Okay. So hold a pen or pencil in front of you and close one of your eyes. So you may see it at one point. Now you close close the other eye, you can see the shift of points in it. That is, first you may have seen your point here, but when you close your next eye, you may see it somewhat away. I mean, not in the same place, but some kind of shift you may observe. That is, let it be, that point will be B. So this AB is known as basis. So in general, we can say that this A and B is known as point of observation. This A and B. Okay. So the distance of this, I am holding it right in front of me. So if my marker is here, if I keep it here, so this is the distance D. Coming back to our problem, suppose I am considering Earth. So let this be point A, let this be point B. Let the star or planet be here. So this point is S. So this point is D. Let the distance between A and B be small letter b. The length of the base is B. Yeah, there is an angle theta. Okay. Now you will be getting an idea. Okay. So this is our point AB. This is our planet Earth. This is the star. We want to measure this distance. Okay. So coming back to this figure, B by D will be very much less than 1. Why? Because AB is the 2 points within the Earth, but this D is very much far away from the Earth. It's in the, like, it will be very much far away. So this B will be obviously less than, the numerator will be less than the denominator. So obviously it will be less than 1. Understood? Also, theta is very small. Now, we are considering this as a part of our circle. Part of a circle. This we are considering it as an arc of a circle. That is, see, if this is my AB, so this will be the center S, this will be B. Okay. Every approximations which we are making, in generally, if we are speaking about it, it's for our sake of understanding or for the simplification. So in this case, these are not the same figures, okay? This is the figure which we require. In this figure, we are doing all the calculations. So for your understanding, I have drew a Earth and a star. Here it's like, if you complete a circle like this, it will be an arc of the part of the arc of a circle. So now we are considering it from here. So the arc AB, if you are considering this arc length, A is equal to BS. Then AB is equal to d theta. AB is equal to d theta. We know that this B is equal to d theta. From this, we can find the distance d. D is equal to b by theta. So, to find the distance of any faraway object like stars or planets, we can use this. Now you have the distance. You know what is the distance of that planet from the Earth. Since you know this, you can also find the angular diameter d of that faraway object. For that, we already know what is this d. So, alpha is equal to d by d. This you have already found. This is the one which we have to find. So, alpha is the angle made from the Earth. That is this alpha. Angle measured from the Earth. That is its alpha. You know this d. The substitute so that you will get d. Sometimes the problem may ask like if the distance between two observatories is some kind of some 60 kilometer, and if this angle is given, you can find d. And if they ask to find the diameter, angular diameter, using this formula. So that's about the parallax method. Now, the size of the object we come across in this universe vary over a wide range. It varies from 10 to the power minus 14, which is the size of a nucleus, to 10 to the power 26, which is the size of the extent of observable universe. There are some special units which we use to represent the length, that is Fermi. One Fermi is equal to 10 to the power minus 15 meter. One angstrom, which is equal to 10 to the power minus 10 meter. One astronomical unit, which is equal to 1.496 into 10 to the power 11 meter. One light year, 9.46 into 10 to the power 15 meter. You should not confuse this light year with time. Even though year is there, year is here, it's still a unit of length, not the unit of time. Keep in mind. Same way, 1 parsec is equal to 3.08 into 10 to the power 16 meter. And these are normally used in astrophysics. These units are normally used in astrophysics, and these units are normally used in atomic subatomic levels. So these are some basic thing about length. Now we'll go on to mass. Talking about the measurement of mass, like if I ask you to weigh something like your mobile phone or your mass, you may weigh it in your weighing machine or the one which we use in grocery shops and all. But what if I ask you to measure the mass of some planets or stars or some particles like atoms, molecules? In such cases, you can't take some atoms and you can't weigh it in a weighing machine. So we use certain techniques for measuring such masses. For measuring masses of planets, stars, etc., we are using gravitational methods. And for measuring the mass of atoms, molecules, or any subatomic atomic particles, we use mass spectroscopy. So about these things and all you will learn in detail later. Now we will go to important thing, that is error precision and accuracy. In today's class, we'll mainly concentrate on these two, precision and accuracy. Measurement is the foundation of all science and technology. For example, if I'm asking you to measure the length of certain thing, let me say I have given you a wire, and if I am asking you to measure, like if I'm asking to measure the length of that wire to 5 different people, some may tell it as 10 centimeter, other may tell it as 10.1 centimeter, some may get it as 9.1 centimeter, some may get it as 10.2 centimeter, 9.8 centimeter. So these are the different types. I got different values for the measurement of one same wire, which I gave it to 5 different people. So this uncertainty in measurement is known as error. Error is the uncertainty in measurement. Whatever experiment you do, whatever big or small experiment you do, this error is an inevitable factor. This error will be there all the time, whether it is in computer or some real life experiment or whatever, this error will be always there. Different types of errors are there that we will go into details in this chapter only, but in the next part of the lecture. Moving on to precision and accuracy. What do you mean by precision and accuracy? There is a marker. This is the marker. I am asking 3 people to measure the length of this marker. Suppose the true value or the actual value of this marker is 12.516 centimeter. This is the true value. Okay, I'm asking 3 people to measure the length of this marker. So first person got the measure as 12.39 centimeter. Second got it as 12.5 centimeter, and third one got it as 12.3 centimeter. Okay. So among these 3 people, who will be more accurate? The one which got 12.5 centimeter will be more accurate. Why? Because this is close to the true value. Accuracy actually gives us like how close is our value to the true value. So among the 3 measurements, this 12.5 centimeter is close to this. So this is more accurate. More accurate. Even though this is more accurate, this is less precise. The first one who measured it as 12.39 is more precise. Why? Because he was able to measure till 2 decimal points, whereas the rest 2 measurements are only till 1 decimal point. Even though this is more accurate, because this is close, this is among all the 3 measurements, this measurement is close to the true value. So even though this is more accurate, but less precise. Here, even though this is more precise, This is less accurate. So that's it for the session. We will end by this for today's session. In the upcoming videos, upcoming parts, we will be discussing about error, different types of errors, dimension analysis and significant figures. So if you have any doubt, please do comment in the comment box. Stay tuned and thanks for watching.
GeopByte.